Good evening, all of you.
Good evening, sir.
Good evening, sir.
Good evening.
Shall we start our class?
Yes, sir.
Yes, sir.
Yes, sir.
Just a minute. See, is my voice audible?
Yes,
Yes,
sir.
sir.
Yes, sir.
Sure.
Okay. Are you getting a screen? Can anybody read what is there on the screen?
Ashok.
Compound.
Name the topic.
Halogen.
Okay. I request all of you, please keep mute. Otherwise, I have to mute all. Okay. Okay, today's topic, my name is Ashok Alishala, Assistant Professor of Chemistry, Kakatiya Government College, Hanamkonda. So today's topic is the halogen compounds. We are getting 1 or 2 questions from this topic in all MSc Chemistry entrances. Not only in CPJET, it is also in JAM or CU set, or those who are attending for this session from Andhra Pradesh also, APPG set also. There will be 1 or 2 questions from this topic definitely. Okay, this is the today's topic. Let us see. Now, what are the halogen compounds? Let us see. Do you know haloalkanes and haloarenes persist in the environment? Means that will be these halogen compounds was there in the what do you say? Haloalkanes and haloarenes. Haloarenes means benzene ring compounds persist in the environment. Haloarenes were used as herbicides during Vietnam War for defoliating the jungles and making it easier to fight in the war. These haloarenes cannot be decomposed by and broken down by microorganisms like bacteria. As a result of which, it is still intact in the soil of the jungles to this day also. This was used in Vietnam War. Now, let us see. Do you know haloalkanes containing halogens like chlorine, bromine, and iodine are threat to the atmospheric ozone? And another one of the very common examples of the haloalkane compound that lead to the ozone depletion is, I think you know that is chlorofluorocarbons. We might have come across haloalkanes and haloarenes several times in our day-to-day life, as well as industries for various applications.
Slides move అవ్వట్లేదు sir.
You're not moving slides.
First slide ఉన్నది sir.
అవునా? అయ్యో. Okay. ఇప్పుడు ఏమైనా మారిందా?
No sir.
No, sir.
Okay, first I'll stop sharing and again I will share. ఇప్పుడు ఏమైనా కనిపిస్తుందా?
No sir. No sir.
ఏమైనా వచ్చిందా మీకు షేరింగ్ లో? రాలేదు కదా?
ఏం లేదు సార్. మీ స్క్రీన్ కనిపిస్తుంది.
ఒక్క నిమిషం. కనిపిస్తుందా ఏమైనా?
First slide కనిపిస్తుంది.
టాపిక్ కనిపిస్తుంది సార్.
ఓకే, ఫస్ట్ స్లైడ్ అయితే కనిపిస్తుంది కదా? ఇప్పుడు చూడండి ఒకసారి. ఇప్పుడు కనిపిస్తుంది ఏమైనా? సెకండ్ స్లైడ్ వచ్చిందా?
లేదు సార్.
ఇక్కడ నా దగ్గర మారుతుంది, మీ దగ్గర మారట్లేదు. Just a minute. ఇప్పుడు ఏమైనా స్లైడ్ కనిపిస్తుందా?
No,
లేదు
sir.
సార్.
నౌ
Sharing. First slide.
టాపిక్ వచ్చింది సార్.
టాపిక్ వచ్చిందా? ఇప్పుడు చూడండి.
ఓకే సార్, నా ఓకే.
Change ayin, sir.
Okay, sir.
Okay.
Moving, sir.
స్లైడ్ షేర్ చేసినప్పుడు మూవ్ అవుతుంది. స్లైడ్ షేర్ మూవ్ అవ్వట్లేదు. అయ్యో, ఎందుకు మూవ్ అవ్వట్లేదు మరి?
వచ్చింది సార్.
అవును వస్తుంది, కానీ ప్రజెంటేషన్ not getting this one.
అవును సార్, ఇప్పుడు స్లైడ్ షేరింగ్ లో వచ్చింది సార్.
ఒక నిమిషం, మూవ్ అవుతుందా లేదా చూసుకుంటాను. ఓకే, నౌ ఇట్స్ మూవింగ్ నా?
ఎస్ సార్.
Yes, sir.
Okay. Okay, just it is an introduction. Just during the Vth number, these haloalkanes, haloarenes are used for the defoliating the jungles and making easier to fight in the war. For the jungles clear చేయడం కోసం దీన్ని యూజ్ చేశారు in this time. And these haloalkanes are not decomposed by any microorganisms like bacteria. As a result, even in nowadays in the Vietnam War, today also these haloalkanes, haloarenes are there. Okay, now do you know all haloalkanes containing halogen like chlorine, fluorine, bromine, iodine are threat to the atmospheric ozone? That you know, those compounds commonly we call it as a chlorofluorocarbons. Now we might have come across haloalkanes and haloarenes several times in our day-to-day life, as well as industries for various applications. Let us know more about these organic compounds. Two names for every compound. Common name. Okay. One is first we are discussing about the nomenclature. There are generally we take the two names for every organic compound. One is said to be the common name, that is our trivial name. In general, we call it like our nicknames. And another one we call it as the IUPAC. Okay, let us see. Naming of the compounds by some set of some rules. We have to find three primary things for naming the compound in IUPAC format. Can anybody tell me what are the three tags or three primary things for naming compound?
Prefix, word root, suffix.
Very good.
Word root suffix.
Okay. Find the parent chain, the compound. This is called longest hydrocarbon. Then next we have to find the functional group. It will form the suffix, and find the substituents and position. It will form the prefix. These are the main important. That is said to be, what we say, one is said to what you have to say, longest hydrocarbon, what is suffix, what is prefix. In addition to these three, you have to remember what is the nature of the bond between the carbons also. That is ane, ene, and ide. Now let us see. The functional group will form suffix or prefix depending on the priority series. This is going to be the priority series. First, we have to give the priority for sulfonic acid, followed by carboxylic acid, followed by ester. That is that is called acid halides like COCl2, then amides, then aldehydes, then cyanides, that is called nitriles, carbonyl compound, that is ketone, and alcohols. Then this is the thiol, amine, alkene, alkyne, nitro compound, and nitroso compound. Then finally we have to give the halogen. That means halogen has the least preference when compared to the all other functional groups while naming. Now let us see. The common name of the haloalkanes is alkyl halide, that you know. Generally methyl chloride, methyl bromide, ethyl halide, like this we call. Alkyl halide is a common name. Then what is the IUPAC nomenclature? In IUPAC nomenclature, what is the numerical position and alphabetically placed as halo, then a root word, and then A for the alkanes. What is that? We have to what is the position of the halogen compound and what is the root word, and finally if it is an alkane, that is carbon-carbon single bond, we use it as a. For example, N-propyl chloride is the common name. Then the position of the chlorinate first carbon, that's why we call it as the 1-chloropropane. Of course, all these things you know, but just a few minutes we will recollect our previous knowledge. And this is at second position, that's why we call it as the 2-chloropropane. And also the common name is isopropyl chloride. And what is the name of this compound? This is N-butyl chloride. N stands for normal. And then we call it as the 1-chlorobutane. And this is isobutyl chloride, or we call it as the 2-chlorobutane. Now what is this one? This is tertiary butyl chloride, or 2-chloro, 2-methyl propane is its IUPAC name. The common names for haloarenes, is aryl halide. IUPAC name in this nomenclature system, the naming of numerical prefixes depends on the basis of the position of the halogen atom in the aromatic ring. If more than one halogen atom is present, the aromatic ring is numbered and the halogen group is named on the basis of the numerical position of the ring. For example, let us take, this is, we call it as a 1-2 position, 1-3 position, 1-4 position, like this. Suppose if this is the compound, this we call it as the 1-iodo-2-methyl benzene. Because we are giving the preference to the halogen, that's why this is the first compound, this is the first carbon, and this is going to be the second. Now, what is the name here? This we have to give the preference to the halogen. That's why this is going to be the 1-chloro, and here this is going to be the fourth position. At fourth position, what is this one? There will be 1, 2, 3. But at a second carbon, there is the methyl group is there. That's why 2-methyl, and total it is a propyl group. 1, 2, 3. This is a propyl group, and here at second carbon there is a methyl. That's why we keep in the bracket 2-methyl propyl benzene. Okay, this is some another. Suppose if the dihaloalkanes having the identical halogen atoms are termed as alkylidene or alkaline dihalides. They can be divided into two types. I think you know, geminal dihalides and a vicinal dihalides. What are the geminal dihalides?
Sir, please explain Telugu also.
Are placed on the same quantum. What is a vicinal dihalides? When the halogen atoms are present on the adjacent carbon atoms. Let us take some example. The first one, CH3, CHCl2. The common name we can call it as the ethylene chloride, and it is an example for gem dihalide. What may be the IUPAC name? Because the first carbon contains 2 chlorines, it is called as because the 2 chlorines are present on the same one carbon, that's a 1,1 dichloroethane. Here this is going to be the 2 chlorine atoms are present on the adjacent carbon. That's why it is called, common name is ethylene dichloride. Because it is an adjacent carbon, therefore it is called as a weak dihalides, or we call it as the IUPAC name is 1,2-dichloroethane. Now let us see what is the classification. The classification here, the based on the hybridization. That is the halogen containing carbon. Based on the carbon having the halogen and its hybridization, they are classified into the two categories. One is said to be the sp3 hybridization carbon, another is said to be the sp2 hybridization carbon. See, in sp3 hybridization, we know primary alkyl halide, secondary alkyl halide, tertiary alkyl halide. And another two is said to be the allylic halide and benzylic halide. You remember this, the last things, allylic, benzylic, vinylic. These are some important, and we oftenly confused regarding this terminology. In primary alkane, you know that the halogen is attached to the primary carbon atom. Whereas in secondary alkyl halide, the halogen is attached to the secondary carbon atom like this. And when in the tertiary alkyl halide, the halogen is attached to the tertiary carbon atom. See, what is allylic carbon? You remember this allylic is nothing but there will be CH2CH double bond, but the halogen is not present at this carbon, but it is present at the third carbon. This is going to be this is the first carbon, second carbon, this third carbon. That means here the double bond is present, that is on beta position, not in the alpha position. This is going to be the alpha, this is going to be the beta. And like this group is said to be the, if you see this group, I will take pen. And if you see this group is said to be the, what do you say, this is going to be the vinyl. See, this group is said to be the vinyl. For this vinyl group, if you add one more CH2, that is one more carbon, and that is going to be the allylic carbon. This is the vinylic carbon, this is going to be the allylic carbon, this. And if the halogen is present directly to the double bonded carbon atom, that is called vinyl. If this halogen is present here, that is at the third carbon atom, then it is called as the allyl. And you know benzylic halide is, this is going to be the benzylic halide. That means there will be benzene ring, adjacent to there will be CH2. That's why it is called as the benzylic. See, here it is going to be the aryl halide. This is halogen here attached directly to the benzene ring. Whereas here, between the benzene ring and halogen, there is some aliphatic carbon atoms will be present. That is called as the benzylic carbon, and this will be called as the arylic. Can anybody unmute and tell me what is the name of these compounds? Now I am writing here. Here it is going to be the, I am writing here. Can anybody name? This is Cl. I am taking another one.
Orthochlorobenzene.
No, just a minute. And there will be another one I am
Chlorobenzene, sir.
writing like this. And here this is going to be the here chlorine. And one more I am writing here. This is going to be. Can anybody tell me what is the name of the first compound? CO here.
Parachlorobenzene.
What is the name of this compound? This is
Chlorobenzene.
this is called as 2-chlorobenzene or benzyl chloride, normal benzyl chloride, normal, not like this. This is, we call it as the chlorobenzene. Okay, this is we simply call as the chlorobenzene. What is the name of this compound?
Methyl chlorobenzene.
Huh?
Benzyl chloride.
Benzyl chloride, sir. Benzyl
Benzyl
chloride.
chloride is right. Benzyl chloride is the right name. Can anybody tell me what is the name of, okay, benzyl chloride. This is going to be the benzyl chloride. Can anybody tell me what is the name of the third one? This one. This is CO. This is COCl.
Benzyl chloride, sir. Benzyl chloride.
Yeah? Benzyl?
Chloride. Benzyl chloride.
Can you tell me once again?
Benzyl chloride, sir.
Yes, you are right. See the difference.
BNZO YL, sir.
Very good. I want to tell you this difference. This is going to the benzyl chloride. This is whereas it is benzoyl chloride. Okay. This is chlorobenzene, benzyl chloride, benzoyl chloride. Okay. this difference you remember, because most of us are getting confused between this terminology. That's why I took this. They can be classified on the basis of number of hydrogen atoms also. Compounds with sp3 CX bond, just now we discussed. Compounds having sp2 CX bond, this just now we discussed. On the basis of the number of hydrogen atoms, they can be divided into the mono, di and poly, that is tri, tetra and so on. Compounds of haloalkanes and haloarenes. It is named depending on the number of halogen atoms these compounds contain in their structures. I'll tell you some example. This is called mono haloalkane, isn't it? Because there is only one halogen is present. This is called dihaloalkane. Is it dihalide or weak dihalide?
Vicinal.
It is vicinal dihalide. Next, other one is, this is trihaloalkane. That is, there are 3 halogens at present. And examples, this is monohaloarine, dihaloarine, trihaloarine. That is in mono, that is, it is dihaloarenes are 1, 2 position, trihalogens are here. If you see the position 1, 2, 3 positions. Now, monohalo compounds can again be classified into the and subclasses on the basis of hybridization of the carbon atom to which halogen atom is attached. Just now I told you that is primary, secondary, tertiary, and so on. Compounds with sp3 CX bond, here X is the halogen compound. These compounds can be further divided into 3 types, that is called as the alkyl halides. In this class, the halogen attached to an alkyl group. And the general formula, we can write it as a CnH2n plus 1x. That means it is an alkane. They are further classified into the mainly 3 types of on the base of the carbon atom, to which the carbon bearing halogen is primary, secondary, and tertiary. Just now I told you. This classification is based on the nature of the carbon atom to which the halogen atom is attached, whether it is a primary, secondary, or tertiary, like this. This is going to be the primary because this is attached, this carbon. We are looking for this carbon because the halogen is attached to this carbon. That's why this carbon is attached to only 1 carbon atom, that is alkyl group, whereas here 2 alkyl groups, whereas here 3 alkyl groups. That's why primary, secondary, and tertiary. Another important is the allyl halides. That is alkyl halide. This is allyl halides. This classification compound is found by the bonding of halogen group having sp3 hybridized carbon atom present next to a carbon-carbon double bond structure. Let us see. The carbon-carbon double bond structure is also known as allylic carbon. Thus, the name is allylic halide. This is going to be the, here up to here, if you see, this is going to be the allyl. This is, okay, this carbon is said to be the allylic carbon. That's why it is called as the allylic halides. Now, what are the vinylic halides? Here, the vinylic halides is the carbon is sp2 hybridized, whereas see here, what is the difference between these two? In allylic halides, the halogen is attached to this carbon where the hybridization is sp3, whereas in vinylic halides, the carbon is attached to this carbon atom.
sp2.
It is sp2 hybridized. Can you tell me, is it allylic or vinylic?
Allylic, sir.
Allylic, sir.
Very good. This is going to be the allylic. This is going to be, this is the vinyl. But whereas here, this halogen is, this carbon is not sp3 hybridized, it is adjacent to the carbon-carbon double bond. That's why it is allylic halides. Now, benzylic halides. Just now we discussed this benzylic halides. This is going to be the benzylic halides where between the benzene ring and halogen, there will be some a chain, that is alkane chain will be there. That is called as the benzylic halides. Compound having sp2 CX bond. Just now we discussed this is. Now, can you tell me? Okay, this is some repetition examples. Can you tell me what is the nature of this? That is alkyl halide. Is it vinylic or
Vinylic. Vinylic.
Vinylic, sir.
This is going to be the vinylic. Okay. Now, aryl halide. Just now, this also just now I told you. This is aryl halide. Because all you know, that's why I'm skipping this one. See, what is the name of this compound? write down the structure of the, okay, you should have some notes with you, rough notes or something. Perfluorobenzene. Actually, I revealed that structure also. Perfluorobenzene structure. What may be the perfluorobenzene structure? This is going to be the perfluorobenzene structure because all fluoride. Can anybody tell me what may be the molecular formula of this compound?
C6 F6 sir.
C6H6F6.
C6F6 is right. C6F6 is the right answer. Okay. ఈ కొంచెం ఫాస్ట్ గా ఎందుకు చెప్తున్నానంటే ఆల్రెడీ ఇవన్నీ నామినిక్లేచర్ కాబట్టి కొంచెం ఫాస్ట్ గా చెప్తున్నాను. ఎవరు మెసేజ్ పెట్టారో స్లోగా చెప్పని. ఇవంతా నామినిక్లేచర్ కాబట్టి దీన్ని ఎందుకు అనవసరమైన టైం స్పెండ్ చేయడం అని కొంచెం ఫాస్ట్ చేస్తాను.
కొంచెం తెలుగులో కూడా ఎక్స్ప్లెయిన్ చేయండి సార్.
ఓకే. Can anybody tell me what may be the name of this compound? పెన్ పేపర్ దగ్గర పెట్టుకోండి, మీరు రఫ్ వర్క్ కూడా చేస్తూ ఉండాలి.
1 bromo 2 chloro 3 chloro butane. 1 bromo 2,3 dichloro 1 bromo 2,3 dichloro butane.
Butane.
Dichloro. 1 bromo 2,3 dichloro butane, sir.
1 bromo 2,3 dichloro
butane.
butane because it is a 4 carbons.
Butane.
1 bromo 2,3 dichloro butane is the right answer. Now what is the name of this compound?
1 iodopropane.
This is 1 iodopropane. Don't say iodopropane because if there is more than 2 carbons, you should indicate the position of the halogen. 1 iodopropane. What may be the name of this compound?
Cyclofluoropentane.
What may be the name?
Cyclofluoropentane.
Any?
Cyclopentane.
Any other answers?
1 fluorocyclopentane.
This is fluorocyclopentane because there is no need of writing the position because the fluid is present here or here or here or here, anywhere in this. That is, there is no change. No need of saying here 1. That's why simply we can say fluorocyclopentane. What may be the name of this compound?
Tertiary iodides.
That is common name. What may be its IUPAC name?
2 butyl iodide. 2 methyl.
Neopropyl iodide. Is it neo?
Isomethyl iodobutane.
Wrong. I am asking you IUPAC name.
2 methyl propane.
Very good. 2 iodo 2 methyl propane. Because in the case of the UPAC name, first we have to select the longest chain. This is going to be the longest chain. This is the first carbon, this is second carbon, this is third carbon. Therefore, at second carbon, there will be methyl group and iodine. That's why it's 2 iodo 2 methyl propane is the right answer.
2 methyl
Propane is the right answer. What may be the name?
2 comma
Dibromopentane.
Pentane, sir.
Okay, pentane.
2,4 dibromopentane.
2,4
Dibromopentane.
dibromopentane. 2,4 dibromopentane is right answer. Parachlorotoluene is a common name. What is its IUPAC name?
Methyl chlorobenzene.
That is also not
Chloromethyl benzene, sir.
4 methyl chlorobenzene, sir.
very good. It is a 4
4-methyl
methyl.
sir.
4-chlorotoluene. 4-chlorotoluene or 4-chloro. No, not 4-chloro. 4-methyl chlorobenzene. Sorry. what we say, this is 1 chloro.
Sir, ఒకసారి
Because
explain
it
చేయండి
is
ఎట్లా?
preference, 1 chloro 4 methyl benzene. 1 chloro 4 methyl benzene. You know the toluene is nothing but the methyl benzene is called as a toluene. That's why it is called 4 chloro toluene. Okay, not that is completed. I will take another slide. Yes. Slide వచ్చిందండి మీకు?
ఎస్ సార్, మూవ్ ఆన్ సార్.
ఓకే, జస్ట్ ఒకసారి మళ్ళీ ఒకసారి మూవ్ చేస్తాను. స్లైడ్ షేర్ వచ్చిందా?
లేదు సార్,
చేంజ్ అయిందా ఏమైనా?
ఏం కాలేదు సార్,
No, sir.
ఓకే.
ఇంట్రడక్షన్ ఉంది సార్.
Sir, can you share this PDF in the group, sir?
ఏమ్మా? I will share. No problem.
Thank you, sir.
మీకు ఇది స్లైడ్ షేర్ అయిందా?
లేదు సార్,
స్లైడ్ రాలేదు.
కావట్లేదు సార్, లోడ్ అవుతుంది.
లోడ్ అవుతుందా? ఓకే.
లేదు సార్, లోడ్ ఇప్పుడు వచ్చింది సార్.
వచ్చిందా స్లైడ్?
లేదు సార్, మళ్ళీ
చేంజ్ కావట్లేదు సార్ స్లైడ్.
మళ్ళీ
నేను
introduction
చేంజ్
వచ్చింది
చేయలేదు
సార్.
ఇంకా నేను చేంజ్ చేయలేదు.
ఓకే సార్.
ఎందుకు ఒక్కోసారి షేర్ అవుతుంది, ఒక్కోసారి అవ్వట్లేదు. Presentation. Sometimes this technical problem arises. Be patient.
లేదు సార్, మళ్ళీ సేమ్ సార్.
మళ్ళీ సేమ్ వచ్చింది. ఒక్క నిమిషం. ఏం లోడ్ కావట్లేదు కదా?
మళ్ళీ సేమ్ సార్. ఇంకా
I'm trying this. మీకేం షేర్ కాలేదు, ఓన్లీ స్లైడే వచ్చింది కదా మీకు?
అవును సార్.
ఇందాక వచ్చింది మళ్ళీ ఇప్పుడు బంద్ అయిపోయింది.
స్లైడ్స్ ఏం రాలేవు సార్.
వచ్చినాయి కదా, స్లైడ్ వచ్చినాయి కదా.
స్లైడ్ షేర్ లో రాలేదు సార్.
అదే స్లైడ్ షేర్ లో వస్తుంది కదా, చూస్తున్నా.
స్లైడ్స్ రాలేవు సార్.
జస్ట్ పీపీటీ ప్రెజెంటేషన్ వచ్చింది మీకు.
ఎస్ సార్.
ఇక్కడేమో వస్తుంది, మీకేమో రావట్లేదు.
రాలే.
ఓకే, ఎనీహౌ ఇలా చేంజ్ అవుతుందో చూడండి ఒకసారి. ఇలా స్లైడ్ మారుతుందా మీకు?
No, sir.
ఓకే సార్, మారుతుంది.
ఇలా మారుతుంది కానీ అలా వస్తలేదు కదా. సరే, లెటర్స్ హ్యావింగ్ లైక్ దిస్.
సార్ ఇప్పుడు కనిపిస్తుంది సార్.
కనిపిస్తుంది కానీ మనకి అదేంటి
స్లైడ్ చేంజ్ కావట్లేదు సార్. ఇప్పుడైతే కనిపిస్తుంది, స్క్రీన్ అయితే కనిపిస్తుంది సార్.
స్క్రీన్ మీద కనిపిస్తుంది కానీ స్లైడ్ షేర్ లాగా రావట్లేదు.
ఓకే సార్, ఇలా అని చెప్పుకుందాం సార్.
ఓకే సరే, ఇది అది ఏదో టెక్నికల్ ఇష్యూ ఉన్నట్టుంది, ఇందాక లాగా చెప్తున్నాము. ఓకే, జనరల్ గా నేను స్లైడ్ పెట్టేసి చెప్తాను మీకు. Okay, this is going to be the second session. Chemical reactivity of halogen compound, formation of the first one we have to discuss here, the formation of the Grignard reagent. In chemical reactivity one, and another one is the formation of the Grignard reagent. Let us take the first one. Are you getting slide changing the other?
Yes, sir.
Yes, sir. Sir.
First, let us discuss about the. మీకు కావాలంటే
No,
కొంచెం
sir.
మీరు జూమ్ చేసుకోండి, క్లియర్ గా కనపడాలంటే. ఎందుకంటే అది టెక్నికల్ ప్రాబ్లం తోటి మనకి ఇది వస్తలేదు, ఫుల్ షేర్ వస్తలేదు, స్లైడ్ షో వస్తలేదు. ఇది చిన్న టెక్నికల్ ప్రాబ్లం ఉన్నట్టుంది. ఓకే, లెట్ us see the chemical reactivity of halogen compounds. Sometimes you will get a question like this: among the following halogen compounds, which is more reactive, which is less reactive, or arranged in the increasing order of their reactivity, or are arranged in the decreasing order of the reactivity? Like that questions will may arise. Okay, first let us see what are the types of reaction that undergo by these halogen compounds. One is said to be the nucleophilic substitution reaction, other is said to be the elimination reaction. What is nucleophilic substitution reaction? It is nothing but like a cocoa cake. One halogen is substituted by another group, or another one is said to be the nucleophilic substitution, like our cocoa cake. What is elimination reaction? During the elimination reaction, what happened? A byproduct is also formed. That means elimination is a result in the formation of from carbon-carbon single bond to the carbon-carbon double bond. Let us see this one. Nucleophilic substitution reaction. The halogen bond, the bond in a halogen compound is a polar bond. That is the carbon and halogen. Here it is a carbon is there, and here it is halogen is there. Are you seeing here? Okay. Here this is going to be the carbon and this is going to be the halogen. Because of the difference in the electronegativity between the carbon and halogen, and it is a polar in nature because of the higher electronegativity of halogen over the carbon atom. This can be represented as what is called this bond length is greater than this bond length, and it is going to be the X minus. The carbon CX bond is partially positively charged, hence shows acidic property of electron deficient atom or electrophilic character. So it is readily attacked by the nucleophile. That is, halogen compounds readily undergo nucleophilic substitution reactions. Okay, for example, this is a halogen compound, alkyl halide. This is a nucleophile, and this will be substituted by this. Okay, I will give you an example here. Actually, all these are in the animation. If we get the slideshow, we get very attractive. And here, this is going to be the elimination. This is going to be the nucleophilic substitution reaction, where one nucleophile is substituted by another nucleophile. Whereas here it is an elimination. Elimination is here halogen is eliminated from one carbon, and some hydrogen or other atoms is eliminated from the beta carbon. That's why if the this is called as a beta elimination reaction. If beta hydrogen is present, they are acidic in nature. So in the presence of a strong base and under suitable condition, they may be undergo elimination reaction. For example, dehydrobromation of the ethyl bromide in presence of alcoholic KOH, you can see. Here this OH minus will take this hydrogen. The same time what happened, this bond between the carbon and hydrogen, this bond is shifted to between these two carbon atoms. Then the simultaneously the bromine is removed. Therefore, the Br minus, this H is taken by OH minus, that's why it is going to be the H2O. Here what happened, because this bond is shifted to here, this bond is removed. That's why it is results in the formation of carbon-carbon double bond. That is, in elimination reaction, the carbon-carbon single bond become to the carbon-carbon double bond. Now, a reduction reaction. What are the reduction reactions? See, alkyl halides when reduced with a nascent hydrogen produces alkanes. There are the different reagents that can produce the repeat cheymanari. That is no here. Actually, there is no need of much explanation for this nucleophilic substitution reaction and elimination. Nucleophilic substitution reaction is like a Coco game, and all of you know Coco game. But Coco game andariki telisi untundi. ఏంటి ఒక ప్లేయర్ వచ్చి ఇంకో ప్లేయర్ కి కో ఇస్తారు, దెన్ దట్ ప్లేయర్ విల్ మూవ్. అలాగే ఇక్కడ కూడా ఏమవుతుంది, ఒక న్యూక్లియోఫైల్ వచ్చి ఇంకొక న్యూక్లియోఫైల్, హియర్ ఇట్ ఈస్ హాలోజన్, దట్ విల్ బి సబ్స్టిట్యూటెడ్. దట్స్ వై ఇట్ ఈస్ కాల్డ్ nucleophilic substitution reaction. We will discuss in detail about this nucleophilic substitution in SN1 and SN2 also. ఎలిమినేషన్ లో ఏమవుతుంది, హాలోజన్ ఏ కార్బన్ మీద అయితే ఉంటుందో హాలోజన్ పక్కన అంటే బీటా పొజిషన్ లో ఉన్న కార్బన్ పై నుంచి ఇంకొకటి హైడ్రోజన్ రీప్లేస్ అవుతుంది, అంటే ఎలిమినేట్ అవుతుంది. కాబట్టి దీన్ని ఏమంటాం అంటే బీటా ఎలిమినేషన్ అంటాం. ఆల్ఫా ఎలిమినేషన్ అంటే ఏంటి, ఆల్ఫా ఎలిమినేషన్ ఈజ్ నథింగ్ బట్ వాట్ యు సే,
ఆల్ఫా కార్బన్ హైడ్రోజన్.
మళ్ళీ ఇది పోయిందండి, ఒక్క నిమిషం. రావట్లేదు, ఒక్క నిమిషం, మళ్ళీ దట్ వాస్ గాన్. ఓకే, హియర్ నేను ఏదైనా రాద్దామని ట్రై చేస్తే అది ఏమవుతుందంటే వెళ్ళిపోతుంది. ఓకే, హియర్ వాట్ హ్యాపెన్స్, హియర్ ఆల్ఫా ఎలిమినేషన్ అంటే ఇదే కార్బన్ మీద హాలోజన్ హైడ్రోజన్ కూడా రిమూవ్ అయితే దాన్ని ఆల్ఫా ఎలిమినేషన్ అంటాం. అండ్ కనిపిస్తుందా మీకు, స్లైడ్ కనిపిస్తుంది కదండి? ఓకే, suppose if the halogen is removed, eliminated from one carbon, and if the hydrogen is removed from adjacent carbon, that is called beta elimination. Here this is a beta elimination reaction. Let us take some other reaction that is called reduction. Alkyl halides when reduced with nascent hydrogen produces alkanes. There are 5 reducing agents, and here what is it? Zinc and hydrochloric acid, hydrogen and red phosphorus, lithium aluminum hydride. LiH means lithium aluminum hydride. magnesium and H2O. Here, this is going to be the H2O. Otherwise, I will write this H2O. This is going to be the H2O. See, among this any reagent, either ZnHCl or hydrogenated phosphorus or lithium aluminum hydride, this is going to be the what we call magnesium in water. That these 1, 2, 3, 4 reagents will, what happens? They produces nascent hydrogen, and that's why the hydrogen and H will be removed. Therefore, we'll get the alkane. And here ethyl bromide. When ethyl bromide is treated with the hydrogen iodide and red phosphorus, you'll get the ethane. See, in addition to this, another one is we can have the zinc copper coupled sodium and ethyl alcohol may also used as a reducing agent, which can generate this nascent hydrogen. That's why all these reducing reagents can convert alkyl halide into the alkane. Now let us see this one. See, this is alkyl halide, Zn and HX. HX is nothing but any halogen acid. Alkanes can be prepared by the reduction of alkyl halides with the help of the different methods. Reduction by dissolving metals. An alkane is prepared or produced when zinc reacts with alkyl group in the presence of aqueous acid such as hydrochloric acid or acetic acid, like this. Alkyl halide, Zn and HCl indak man cheppunnam kada, that is going to be this alkane. Now let us see, this is going to be an example. Alkyl halide in presence of Zn and HCl, you will get alkane. And similarly, what is the reaction that involved? What is the mechanism that is involved? Here, the reduction is the transferring of electron from metals to the substrate. Metals to the substrate, followed by the transfer of proton from the acid. See here what actually happened. Zinc, you know, it is an oxidized Zn+2 and loses 2 electrons. These two, among these 2 electrons, before going to this, adding these 2 electrons, and here alkyl halide undergo, what is here? It is a free radical and a chlorine free radical. Here, this is going to be this free radical take 1 more electron and we will get the negatively charged one. And this negatively charged one now reacts with this HCl, and because it is a negatively charged, you take the proton, that is H plus ion, and you will get RH and you will get the Cl minus. And like this 2 Cl minus you taken by the Zn+2 and you will get the ZnCl2. Like this, that means here the Cl minus ion is taken by the Zn+2 and it converts into the ZnCl. Like this, by the transferring of electrons from metals to the substrate, that this is going to be the substrate, and this reduction is carried. Now let us see this one. Reduction by lithium aluminum hydride. ఇక్కడ మనం గమనించాల్సింది ఏంటంటే reduction in presence of ZnHCl, it is carried by the transfer of electron from metals to the substrate. Whereas the reduction in presence of lithium aluminum hydride, here there will be hydrogen transfer. Reduction by lithium aluminum hydride is readily reduced primary and secondary alkyl halides to alkanes, while tertiary alkyl halides gives alkenes. Remember, primary, secondary gives alkanes, tertiary will gives alkenes. Here, this is the direct addition of the hydride hydrogen to this one. That's why we'll get this one, alkane. Now another one, some examples. This is okay. This is going to be the lithium aluminum hydride. Hydrogen is transferred to here, alkane, and you will get the ALH3. That means what you have to remember here, 1 mole of lithium aluminum hydride can produce 1, 2, 3, 4 moles of alkyl halide. That is, 1 mole of lithium aluminum hydride can reduce 4 moles of this alkyl halide. That's why you'll get these 4 molecules. Now let us see a reduction by hydrogenolysis, directly hydrogen in presence of a catalyst. And alkanes can be prepared by the hydrogenolysis, like hydrolysis. This is hydrogenolysis, that is reaction with hydrogen is called hydrogenolysis of alkyl halides in the presence of palladium and charcoal used as a catalyst. And simply hydrogen is transferred to the alkyl halides, you will get this alkane. Now, what is meant by a Grignard reagent? RMGX is said to be a Grignard reagent. Let us see formation of the Grignard reagent. Grignard reagent has a formula RMGX where X is a halogen and R is an alkyl halide or aryl based benzene ring group. For the purpose of this page, we shall take the R to be an alkyl group. And this R may be sometimes aryl group also, but we are taking now only alkyl group. A typical Grignard reagent is ethyl magnesium bromide. Now let us see how the Grignard reagent is formed. Grignard reagents are made by adding the halogenoalkane to the small bits of magnesium in a flask containing ethoxyethane. Ethoxyethane is nothing but diethyl ether. The flask is fitted with a reflex condenser and the mixture is warmed over the water bath for 20 to 30 minutes. You remember one important point here. For the preparation of the Grignard reagent, and there must be there must be the dry conditions must be dry. There should not be a small moisture also, and that's why we use it as a the diethyl ether as a solvent. Okay, now let us take here how does it is formed. Okay, the mechanism of the formation of the Grignard reagent is shown in the below. Like other reaction considered in this, it is also involved a radical intermediate. There is one major difference, however, Grignard formation does not involve a radical chain mechanism. It is a non-chain radical mechanism. Here, this is you're going to see. Magnesium in its valence shell having the 2 valence electron, because you know it is atomic number is 12, and therefore there is a that is 1s2 electron will be there. That is 2s2 electrons are there, 2 electrons in s orbital. And here what happened? These 2 electrons here, X is, this is homolytic cleavage is found here, between here homolytic cleavage. Are you getting here? Okay, here it is homolytic cleavage. 1 electron is taken by the alkyl group, another electron is taken by the halogen. That's why we take the magnesium. Therefore, magnesium here it is get the positive charge. 1 electron is taken from magnesium, another electron is taken from this bond. That's why this is going to be the X minus, and magnesium is the 1 positive charge, 1 unit of positive charge. Then again this free radical will give the this will be shared. This free electron and this free electron will be shared between the alkyl group and magnesium, and you will get the RMGX. This is going to be the mechanism. Formation of the Grignard reagent. Note that the first step is rate determining and involves the transfer of 1 electron from magnesium, which has 2 electrons in its valence shell, to the carbon halogen bond. This forms Mg+1, which is a radical as well as a +1. This is then coupled with the alkyl radical and formed. And diethyl ether is especially a good solvent for the formation of the Grignard reagent, because ethers are non-acidic. Non-acidic means here aprotic. The diethyl ether cannot promote or cannot donate the proton. That's why it is called aprotic. Water or alcohols would be protonated and thus destroy the Grignard reagent, because the Grignard carbon is highly nucleophilic in nature. This would form hydrocarbon. ఒకవేళ మనం ఆల్కహాల్ గాని వాటర్ గాని యూజ్ చేస్తే Grignard reagent form అవుతుంది, then immediately this will be decomposed or reduced to the alkane. That reactions we'll discuss now. This would form the hydrocarbon, but Grignard reagents are stable only in ether. Here, suppose if it is the RMGX, suppose if it is involved any moisture, or if the solvent is used as a water, see the Grignard reagent react with water and form the alkane. Another reason that ethers are good solvent for Grignard reagent is that magnesium halide bond is ionic and thus benefit greatly from being effectively solvated. The formation of ions in very non-polar solvent where they would not be effectively solvated is difficult. That means here, okay, well, water and because it is a polar nature and this is also polar nature, they get be solved. Whereas in the diethyl ether, that polar nature, that is a diethyl ether is a non-polar nature. That's why it is not solved. That is another reason. Formation of the Grignard reagent. Ethers are surprisingly good at solvent cations because the carbon-oxygen bond is relatively polar, thus allowing the oxygen end of the other dipolar to solve it and stabilize the magnesium ion. I will show you here. This is going to be the why the what is called as a Grignard reagent is solvated. In here, the oxygen is more electronegative in nature, and magnesium is going to be the positive nature. That's why the magnesium only this is get solvated, not this halogen. That's why this is get stabilized in the what is called as in ethers. Ethers are okay. This I already told. Okay. Now, for a given alkyl group, the ease of formation of the Grignard reagents is in this order: alkyl halide, alkyl bromide, alkyl chloride. And for a given, okay, for a given, what I meant to say, suppose when these three are treated with the magnesium. For example, alkyl methyl iodide, methyl bromide, methyl chloride is treated with the magnesium. Among these three, methyl iodide is very easily formed when compared to the methyl bromide, when compared to the methyl chloride. Okay, followed this point. This is important for the entrance point of view. For a the magnesium, when treated with the different alkyl halides, the alkyl iodides are more reactive than the alkyl bromides. This is more reactive than the alkyl halides, alkyl chlorides. In the case of the formation of the with the size, suppose the methyl group is there, ethyl group is there, propyl group. The same halogen atom, but different alkyl groups are there. With the increasing the size of the alkyl group, the reactivity will be decreased. The ease of formation of the Grignard reagent is decreased. That is, methyl magnesium iodide is easily formed when compared to the ethyl magnesium iodide. It is easily formed when compared to the propyl magnesium iodide. Okay, followed this point? Are you followed?
Yes,
sir.
sir.
Yes, sir.
Okay. Okay, next. What is the nature of the Grignard reagent? Grignard reagents behaves, it is a dual nature, that is called as the both natures, as a base as well as the nucleophile. Let us take how it acts as a base. It is readily react with the active hydrogen compound to yield hydrocarbons. An active hydrogen compound is one which liberates hydrogen upon treatment with an active metal. That means that is what you say, an active hydrogen compound is nothing but ఏదైనా మనం ఏదైనా ఒక కాంపౌండ్ ని యాక్టివ్ మెటల్ లైక్ సోడియం కానీ మెగ్నీషియం కానీ జింక్ కానీ వీటితో రియాక్ట్ చేస్తే హైడ్రోజన్ లిబరేట్ అయితే దట్ ఈస్ కాల్డ్ యాజ్ ది యాక్టివ్ హైడ్రోజన్ కాంపౌండ్. See, it is acts as a base when treated with the what do you call it as the active hydrogen compound. For example, when Grignard reagent is added to an active hydrogen compound, it simply converts into the alkane and the MgXY. For example, if instead of the Y, if it is OH, assume that instead of the OH, if it is Y, what is that? HOH is nothing but the water. Here, the Y means here OH. Sorry. Y means here OH. That's why when Grignard reagent is treated with either water or with ammonia or with alcohol, then the Grignard reagent results in the formation of the alkane. Now, as a nucleophile, this is as a base. As a base, how do you know this Grignard reagent is a base? Because it reacts with the active hydrogen compound and converts into the alkane. That's why it's a base. Now, how it acts as a nucleophile? It reacts with the electrophilic carbon functions and develops a new carbon-carbon bond. For example, idoka manaki already me carbonyl compounds అయిపోయింది కదా, దాంట్లో how does carbonyl compound react with the Grignard reagent to form the different types of the organic compounds you have learned? I think you know that. కార్బనైల్ కాంపౌండ్ ఆల్డిహైడ్ ఎలా రియాక్ట్ అవుతుంది, ఆల్డిహైడ్ ఎలా రియాక్ట్ అవుతుంది, కీటోన్ ఎలా రియాక్ట్ అవుతుంది, ఫార్మాల్డిహైడ్ ఎలా రియాక్ట్ అవుతుంది, డిఫరెంట్ గ్రిగ్నాట్ రియేజెంట్స్ తోటి. I think you have observed in the while discussing the carbonyl compound by Daynon sir. And here this is the Grignard reagent. When treated with the carbonyl carbon, you will get an alcohol. And different types of alcohols you can prepare by using Grignard reagent and carbonyl compounds. Okay, I will share one more slide. You are not getting no slide sheet. Only slide మాత్రమే వస్తుంది కదా మీకు.
Yes, sir.
Okay, now you got it, no?
ఎస్ సార్, ఇప్పుడు స్లైడ్ షేర్ వస్తుంది సార్.
ఓకే, స్లైడ్ షేర్ ఏదో చిన్న టెక్నికల్ ఇష్యూ ఉన్నట్టుంది. అది డబుల్ క్లిక్ చేస్తే ఒక్కోసారి వస్తుంది, ఒక్కోసారి రావట్లేదు. ఓకే. Okay, continuation, nucleophilic substitution. Okay. Previously, what we discussed is in the previous discussion, that is in second slide share, I discussed mainly what is Grignard reagent, what are the types of reaction that undergone by the this Grignard reagent. Now, in this slide, we will discuss about some nucleophilic substitution reaction. Let us see what is meant by SN2 reaction. Generally, okay, I want to tell you one is, see, okay. The alkyl halides are mainly undergo nucleophilic substitution reactions. In this, mainly there are two reactions. One is said to be the SN2 reaction. S stands for the substitution, N stands for the nucleophilic, 2 stands for the bimolecular. That is, 2 means 2 molecules are involved. That's why it is called bimolecular nucleophilic substitution reaction. And another one we can say that it is going to be the SN1 reaction. That is called, S stands for substitution, N stands for nucleophilic, 1 stands for unimolecular. That's why it is called substitution nucleophilic unimolecular. That is unimolecular nucleophilic substitution reaction. Let us discuss the first one. First, let us see what is nucleophilic substitution reaction. Nucleophile stands for nucleus loving. You know that what are the nucleophiles and what are the electrophiles? What are the nucleophiles and what are the electrophiles?
Electrophile is like
ఎలక్ట్రాన్ డెఫిషియెంట్ స్పీసీస్ సార్.
electrophile is what?
Here,
ఎలక్ట్రాన్ రిచ్ స్పీసీస్ సార్.
nucleophiles are nucleus seeking. That means mainly they consist of negative charge, and electrophiles are electron seeking reagents where they consist of the positive charge. Nucleus stand, that is nucleophile stands for nucleus loving. It is an atom or group of atom that is rich with electron density and reacts or attacks with the electron deficient sites. In the same way, electrophiles are nothing but electron loving. It is an electron deficient atom or group of atoms seeking electrons. Nucleophilicity of a nucleophile depends on the structure. Common nucleophiles are listed here. These are the common nucleophiles. See, this is the nucleophile and the reactivity. Very powerful reactivity. Nucleophiles are iodide, thiol, thiide, and this is the alkyl sulfide. And here 10 to the power of this is going to be the non-minus. It is 10 to the power of, I think, 15. It is missing. This is highly reactive, more than 10 to the power of 4 missing. Sorry. Just a minute. These are powerful nucleophiles. Then good nucleophiles are bromide, hydroxide, alkoxide, cyanide, and azide. This is their reactivity is 10 to the power of 4. You consider it is more than 10 to the power of 4. You remember, digit miss. Then 5 nucleophiles are amine, chloride, fluoride. Then it is going to be the that is carboxylate ion or COO minus. And weak nucleophiles are water and alcohol. And very weak nucleophiles are carboxylic acid. Suppose you are given a question among the following, which is a strong nucleophile among the iodide, bromide, and chloride, fluoride.
Iodide,
What
sir.
is it?
Iodide.
Iodide, like this. Okay. Among this, that's why just now we discussed. Alkyl iodide will be react readily with the magnesium when compared to the alkyl bromide. It is readily reacts with the magnesium when compared to the alkyl chlorides. Okay. Can you remember? I want to tell you one thing here. Mere degree అయిపోయింది కాబట్టి can you see this type of compound anywhere in the organic chemistry? Have you seen this type of compound in the organic chemistry anywhere in your studies? You never find this compound, you remember? You never find this compound because of high electronegativity of the fluorine. It never form Grignard reagent. Only chlorine, bromine, and iodine will form Grignard reagent. Fluorine never form. Okay. See, a substitution reaction where a nucleophile replaces another nucleophile is known as nucleophilic substitution reaction. These substitution reactions are characteristic features of alkyl halides. The induced dipolar nature of the carbon halogen bond. Just now I told you, the carbon among the carbon halogen is more electronegative. Therefore, the carbon halogen bond is polar in nature. Carbon halogen bond creates partial positive and negative charges on carbon and halogen center because it is less electronegative, and you'll get the positive charge here, it will get the negative charge. Here, in the presence of a strong nucleophile, stronger than already attached to the carbon, incoming nucleophile replaces the halogen. See, you can see here it is an RX because it is a polar nature. That's why there will be a positive, partial negative charge on this halogen, and there will be partial positive charge on the alkyl group. And here this Y is stronger nucleophile. This Y must be a stronger nucleophile than this halogen. Then only it will be replaced. Like this, the halogen is attached to the alkyl group, and in the same time, the another halogen, this nucleophile is attached to the alkyl group. In the same time, the halogen is removed. That's why it is called as a leaving group. This X is called as a leaving group, and Y is called as the entering group. Now let us see SN2 reaction. This substitution reaction is greatly influenced by nature of attacking nucleophile or substrate and leaving group. In primary or secondary alkyl halides, attacking of incoming nucleophile and displacement of leaving group takes place in a single step. See here the reactions. This is one important one. In the case of the bulky tertiary alkyl halides, attacking of incoming nucleophile and displacement of the leaving group takes place in two steps. See here, I want to tell you an important point here. The primary and secondary, mainly the primary. This undergo in a single step, whereas the tertiary or bulky tertiary alkyl halides, this undergo two steps. Therefore, simply you can say this undergo, I will tell you again, SN1, whereas this undergo, primary alkyl halides undergo SN2 reaction. Whereas depending on the condition, secondary alkyl halides may undergo either SN2 reaction, depending on the condition, it may also undergo SN1 reaction. But if you take complete this one, primary always undergo SN2, tertiary always undergo SN1. Let us discuss these reactions again. Hence, these substitution reactions follow two different mechanisms. One is called as SN1, another is called as the SN2 reaction. Let us take the first one is the SN2 reaction. A simple example for SN2 mechanism is the reaction of methyl bromide with hydroxide. The attack of incoming hydroxide partially positively charged carbon center displaces the bromide. The formation of new bond of hydroxide ion and cleavage of bromide bond to carbon center takes place in a single step. Let us see here. Actually, the nucleophile pushes off the leaving group from the carbon. The kinetic data suggests that the rate of the reaction is directly proportional to the concentration of both methyl bromide as well as the hydroxide ion. Thus, it is a first order in each reactant and second order of overall reaction. This is going to be happening. The hydroxide ion pushes the bromide. This is going to be the incoming group. The bromide is the what is called as a leaving group. Now we will discuss again the mechanism. See, this is going to be the mechanism. What happened? The rate of the reaction is directly proportional to the alkyl halide as well as the hydroxide. That's why the overall reaction is the second order. That's why it is a SN2 reaction. Let us see here. This is the hydroxide ion attacks on the methyl bromide, and here the bond will be broken between the carbon and halogen bromine, and here there is a partial bond is found between the carbon and oxygen. And this transition state consists of both species. That is, bromide is present and hydroxide is both are present. That's why we can call it as the SN2 reaction. 2 stands for in transition state. Both group, that is the leaving group is present as well as the incoming group is also present. That's why it is called as an SN2 reaction. SN2 reaction is a single step reaction. Only in single step it will be converted into the alcohol product. Therefore, it is a bimolecular reaction where both attacking nucleophile and substrate are involved in the formation of transition state. In this transition state, carbon is bonded to the both incoming nucleophile as well as the departing leaving group. Such a reaction is known as bimolecular nucleophilic substitution reaction. It is denoted as SN2 reaction.
The bond order is 2.
Bond order is to bond order. Okay. An interesting aspect of SN2 mechanism is the 100% inversion of the configuration. Here we are discussing now the stereochemistry. Inversion of the configuration means, suppose if we take what we call it as an optical isomer. If it starts with a D isomer, the product will be the L isomer. Okay. It means incoming nucleophile attacks carbon from the back side, that is opposite side to the leaving group. In the end, incoming nucleophile gets attached to the position opposite to the leaving group. Let us see here. Here, the bromine is removed here. The bromine is now here, it is on the right side. Suppose, imagine here your left and right. For the carbon, the bromine is on the right side. And the hydroxide ion will be attached on the opposite side to the leaving group. And here that what happened in transition state, both are present, that is entering group and another is the leaving group. And here final product, if you observe, the entering group is attached on the back side to the or opposite side to the leaving group. Suppose if it is a D isomer, dextroisomer, the product is a levoisomer will be formed. That's this is called as the inversion. This inversion is called as the Walder inversion. That is, Walder inversion takes place in the case of the SN2 reaction. In the transition state, the reaction center is surrounded by 5 groups and it is sp2 hybridized. The 3 hydrogen atoms are attached to it. Lie in one plane with a bond angle with 120 degrees. The nucleophile and the leaving group are attached to the 2 lobes of the unhybridized p orbital of reaction center. The carbon hydrogen bonds are thus arranged like the spokes of a wheel, while COH and CBr bond, that is carbon hydroxy bond and carbon bromine bond, are along the bond axis. You can see here. Okay. Just I will explain this diagram again. You can see here. Here, the bond angle between these hydrogens is 120 degrees. Okay, sometimes you may get a question like this. What is the hybridization of the carbon in the transition state of SN2 reaction? What is hybridization?
sp2.
20.
What?
sp2, sir.
sp2. But you remember these 2 bonds also there. These are ignored because these are Just it is not a covalent bond, just overlapping of the filled p orbital of the OH with the empty orbital of the carbon. Here also empty orbital of the carbon and electrons of the bromine. That's why these bonds are not considered for the hybridization calculation. Only these bonds are covalent bond and sp2 hybridized, the bond angle is 120 degrees. Okay, now let us see this one. See, the energy profile diagram of SN2 shows the presence of single transition state at highest energy state and no intermediate is formed. The reaction is exothermic in nature. The transition state is highly unstable due to the presence of high energy and 5 bonds around the carbon atom. This is the case. This is going to be the transition state. There are 5 bonds and it is highly unstable. And energy profile diagram, if you see here, this is the starting reactants. This is not products, don't say products. This is the starting reactants. And what happened? This OH, when approaches this methyl bromide, then it is going to be here like this. Okay. And here this will be a transition state. It is higher in energy. And the activation energy of this compound is 102.6 kilojoules per mole. And then again the bromine will be lost, that is bromine will be eliminated or substituted by OH, then you will get the product. See, is it exothermic or endothermic?
Endothermic, sir.
Endothermic.
Endothermic?
Exothermic, sir.
Exothermic, sir.
Tell me, is it exothermic or endothermic?
Endothermic, sir.
Exothermic, sir.
Endothermic, sir.
Okay, see here, I want to clear your doubt. See, this is the energy profile diagram. This is the energy of the reactants. Now, what is the energy of the products? You can assume here this is the energy of the products. Here, let us say energy of the products. Let us say EP. Okay, energy of the reactant. Let us say ER. Which energy is more, ER or EP?
Yeah.
ఈ రెండు ఎనర్జీస్లలో energy of the reactant, energy of the product.
Energy of
Energy
the
profile diagram. Can anybody tell me among these two, which has the greater in energy?
ER.
ER is a greater in energy. Okay. Now here, whenever you remember this point, whenever the greater in energy, ER is when greater than the EP. That means reactant energy is greater than the product. It is always an exothermic in nature. Energy profile diagram చూడగానే exothermic endothermic మీరు చెప్పాలి. ఇప్పుడు చూడండి, this is the energy of the reactant, this is the energy of the product. ఏమైపోతుంది, ఇది ప్రోడక్ట్ నుంచి రియాక్టెంట్స్ నుంచి ప్రోడక్ట్ కి కన్వర్ట్ అయింది. కాబట్టి ఈ మధ్యలో ఎనర్జీ ఏమవుతుందంటే రిలీజ్ అయిపోతుంది. Because this is converted into the higher energy to the lower energy. That's why here this energy will be released. That's why whenever this is the condition, that is always exothermic nature. Suppose energy of the reactant is less than the product. That means here, అప్పుడు ఏముంటుంది మనకి, ఈ ప్రోడక్ట్స్ ఏమో హైయర్ స్టేట్ లో ఉంటాయి, రియాక్టెంట్స్ ఏమో లోయర్ స్టేట్ లో ఉంటాయి. ఇదేమవుతుందంటే లోయర్ ఎనర్జీ టు హైయర్ ఎనర్జీ, అంటే ఫ్రమ్ హియర్ టు హియర్ అన్నమాట. లోయర్ ఎనర్జీ టు హైయర్ ఎనర్జీ అంటే దట్ ప్రాసెస్ ఈస్ ఆల్వేస్ ఇన్వాల్వ్స్ అబ్జార్ప్షన్ ఆఫ్ ఎనర్జీ. దట్స్ వై యు సే దిస్ ఈస్ గోయింగ్ టు బి ఎండోథర్మిక్ ఇన్ నేచర్. This is going to be the endothermic in nature. Okay, I think you follow. By looking at the energy profile diagram, you must say whether it is exothermic or endothermic. Now let us see. Finally, the carbon bromine bond is fully cleaved. The energy required to it partially provided by the carbon OH bond formation. The OH group takes the position of the just opposite to the bromine atom. Just now we discussed that. In SN2, the nucleophile hits the carbon on the side opposite to the bonded to the leaving group. The carbon is said to undergo backside attack. The orbital of the nucleophile overlap with the smaller lobes of the sp3 orbital of the electrophilic carbon. I'll show you there will be one diagram. Hence, the best overlap of the interacting orbital is possible through backside attack only. The best way to visualize the movement of the groups bonded to the carbon at which substitution occurs is to picture an umbrella that turns inside out. This is called Walden inversion. In the window, బాగా గాలి దువారం వేసినప్పుడు బయటికి పోయినా అనుకోండి గొడుగు పట్టుకొని ఏమవుతుంది అంబ్రెల్లా ఇన్సైడ్ అవుట్ అవుతుంది. అలాగే ఇప్పుడు రియాక్టెంట్ నుండి స్టార్ట్ అయ్యి మనం ప్రోడక్ట్కి వెళ్ళినప్పుడు రియాక్టెంట్ కు ఆపోజిట్ కాన్ఫిగరేషన్ తోటి మనకు ప్రోడక్ట్ ఫామ్ అవుతుంది. అండ్ దిస్ ఈస్ వాట్ ఈస్ కాల్డ్ యాజ్ ఇన్వర్షన్ ఆఫ్ కాన్ఫిగరేషన్ అండ్ కామన్లీ కాల్డ్ యాజ్ ది వాల్డన్ ఇన్వర్షన్. Remember what is Walden inversion? Walden inversion is nothing but during the nucleophilic substitution reaction, that is mainly in SN2 reaction of alkyl halides, the configuration of the product is opposite to the reactant. This process is called as the Walden inversion. Like this. This is going to be the inversion of the configuration. The OH is attacked on the back side. These are the lobes of the carbon. This is going to be the transition state. Finally, you will get the configuration is opposite to the alkyl halide. This process is called this inversion is called as the Walden inversion. Okay, now let us see. This is stereochemistry of SN2 reaction. Hence, we can say when SN2 mechanism is operating, the inversion must have occurred. This process often be likened to the turning inside out of an umbrella in a gale. Gale with like this. This is the here. This is going to be the wind flow. Then what happens? Automatically, the umbrella will goes inside out. Inversion of the umbrella similar to the concept of the inversion of the configuration in SN2 mechanism. Hydrolysis of 2-bromobutane. Let us take when 2-bromobutane, that is with R configuration, we will get the alcohol will be S configuration. E minus plus anedi that is not in a mathematical symbols. That is some different. Manam RS nomenclature lo vastundi. There we will discuss again. Hydrolysis of 2-bromobutane like this here. Here, the OH is attacked on the back side. Here, the starting compound is R minus 2-bromobutane, whereas the product configuration is S plus 2-bromobutanol. This is quite opposite. This is R minus. This is going to be S plus. The quite opposite configuration will be formed here. Hydrolysis of 2-bromobutane. Careful observation of the configuration. R minus 2-bromobutane is always gives S plus 2-butanol. Indicates that there is an inversion of configuration from a reactant to the product. Optical rotation plus and minus is or dextro and levo are nothing to do with the configuration. They are measured values, whereas R and S notation indicate the configuration status. This already we discussed. Hydroxide ion is a stronger nucleophile than the bromide. That's why it is replaced. The rate of reaction is proportional to the nucleophilicity. The decrease in nucleophilicity of some nucleophiles in the following are just now. Indaka meeku cheppanu good nucleophiles, strong nucleophiles, weak nucleophiles. Here, the methide ion is a strong nucleophile, then amide ion, then alkyl oxide, hydroxide, bromide, chloride, and fluoride. That's why hydroxide ion can substitute the bromide, bromide can substitute the chloride, chloride can substitute the fluoride. Like this, this will be the order. But you remember, fluoride cannot replace or cannot substitute the chloride. And the reverse process man gurtupetukovali. And the OH can substitute the bromide. Bromide never substitute this OH ions. This is the order of the their nucleophilicity. Then the factor that affect the SN2 reaction is one is the structure of the substrate, that is whether it is a primary or secondary or tertiary, the concentration and reactivity of the nucleophile, and the effect of the solvent, whether we are using the polar solvent or non-polar solvent, the nature of the leaving group. whether the leaving group is the best leaving group or not a best leaving group. That is, it's the nucleophilicity. Okay, and I will give you here. I want to give you one video is there so that you can easily understand. I want to share that video. Okay, see this video. How does it happens? Substitution involving a nucleophile with two species involved in the slowest step. That is called as the rate determining step. See, can you imagine what is this? This is going to be a nucleophile. This is hydroxide. This is oxygen. This is hydrogen. And this yellow colored ball is going to be the bromide ion. Okay, these are now in free state. Both reactants are involved in determining the rate determining step. Okay, now they are getting approaching each other. See what happened. You see the energy. This is the energy of the reactants. When they are come closer to each other, then the energy of the both reactants are increased like this. Okay, then this is going to be the transition state where its energy is very, very high. This energy is very, very high, and the hydroxide ion is attacking on the back side of the bromide ion. This is going to be the bromide ion. Now this is a transition state. Now this is a leaving group. It is leaving in the same time the energy is decreasing. This is going to be the product, and you'll get this is the hydroxide. See here again, you can observe both reactants are approaching and it reaches the maximum energy. It's called a transition state. It is called as a transition state, and then the leaving group leave the transition state. Finally, you will get the product. This is going to be the product, and it was given by the university survey, and we are very much thankful to these people who made this what we call this beautiful animation. Now a simple SN1 reaction is there. Shall we continue for 20 minutes more?
Yeah, okay, sir. Continue.
ఓకే, మనం ఇది ఒకటి టాపిక్ అయిపోతుంది. మనం ఒకవేళ కంటిన్యూ చేసేది ఉంటే సేమ్ ప్రాబ్లం.
Sir, please share this PPT, sir, in the group.
Okay, okay, I'll share, no problem. ఇలా షేర్ అవుతుంది మళ్ళీ సేమ్ ప్రాబ్లం వచ్చింది. You are not getting slides now.
Yes, sir.
ఒక్కోసారి వస్తుంది ఒక్కోసారి మిస్ అవుతుంది. Okay, we are not getting that type of slides. Okay, we don't want to waste time. Okay, now let us take the SN1 reaction. Now getting now, మీరు జూమ్ చేసుకోండి మీరే. స్లైడ్ వచ్చింది కదా మీకు?
Yes,
Yes,
sir.
sir. Continue, sir.
Okay, okay. Let us take the SN1 reaction. I told you already. What is SN1? Nucleophilic unimolecular substitution reaction. Mainly tertiary butyl bromides and does not undergo SN2 reaction. They undergo only SN1 reaction. Like this, the normal reaction is tertiary butyl bromide. Tertiary butyl bromide when treated with the water, and then we'll get the tertiary butyl alcohol. Now, the kinetic data shows that the rate of the reaction depends only upon tertiary butyl bromide, but not on the concentration of the water or hydroxyl layer. The nucleophile water in the above equation does not contribute to the rate of reaction. Adding even a stronger nucleophile does not influence the rate of reaction. The reaction thus follows the first order kinetics, where rate of reaction is independent of concentration and the nature of the nucleophile. It is only depends on the alkyl halide, that is tertiary alkyl halide. Moreover, nucleophile does not participate in the rate determining step. This reaction mechanism is called as unimolecular nucleophilic substitution reaction. That is generally called it as the SN1 reaction. See, the rate of reaction is only directly proportional to the tertiary butyl bromide. Now see this one, the reaction mechanism can be written as, see, this is going to be the leaving group, the step 1. It is a 2-step reaction, whereas the SN2 reaction is only 1 step. Whereas here it is a 2-step. In the first step, it is a slow step and rate determining step, and it is a formation of the tertiary butyl cation and bromide. In the first step, alkyl halide dissociate to form the carbocation and a halide ion. This is a slow step, and it is called as the rate determining step. The formation of the carbocation is a fundamental feature of the SN1 mechanism. Now see, this is going to be the animation lo bounded. Sorry, it's not sharing. SN1 reaction. See here in the step 2, what happened? This is the carbocation. The hydroxide ion now attacks here. Then you'll get an intermediate, tertiary butyl oxonium ion. The carbocation formed in the first step reacts rapidly with the water molecule which acts as a nucleophile. The step completes nucleophilic substitution and forms an oxonium ion. Now here in third step, what happens here? The H plus ion is taken by another water molecule, it converts into the hydronium ion, and you will get the product, as a tertiary butyl alcohol. The last step is fast acid-base reaction. Here water acts as a base and removes the proton from oxonium ion, and to give the final product, that is called as a tertiary butyl alcohol. It is clear that SN1 is a ionization mechanism, whereas SN2 is a association mechanism, whereas SN1 is a ionization mechanism. Now see, this is going to be the energy profile diagram. There are the two steps. See here, there will be two peaks and one depth also. See here, what is this is going to be the reactants, and here the reactant when approaches together, then what happened? Energy of the transition state one will be the higher in energy. Then again it loses the bromide ion and you will get a carbocation, lowers the energy. Then again when OH minus ion approaches the carbocation, again it increases the energy. Then you will get the product to decrease the energy. Finally, what I want to say is, there are the two transition states in the case of the SN1 reaction, whereas in the case of the in SN2 reaction, only one transition state. Among the two transition state one has more energy when compared to the transition state 2. Okay, in between these two, there will be a carbocation that is found, which has a lower energy when compared to the transition 1 and transition 2. Two products are formed when a chiral substrate that possesses an asymmetric electrophilic carbon applied in an SN1 reaction. One of them has the same absolute configuration as a starting product, if according to the CIP rules. The leaving group and the nucleophile leave the same position in the priority order of the substrates, which is called as retention. And indaka manam cheppukunnappudu emaindi SN2 lo opposite configuration of product form avutundi. But here there are the possibility to form the two products. One is retention of the configuration, another is the inversion of the configuration, that we'll discuss here. In contrast to the product possess the opposite and absolute configuration is known as inversion. In SN1 reaction, the nucleophile exists in the substrate before the nucleophilic attack can ever occur. Thus, an intermediate carbocation is then formed. Due to the carbocation is a trigonal planar in shape. Its two enantiomeric sites or enantiotopic sites are susceptible to attack by the nucleophile with the same probability. See here the diagram. See in the first case what happened? This is going to be the first carbon, second carbon, third carbon. Okay. Now here this is going to be a transition state. A carbocation is formed. For this carbocation, this H2O may attack on this lobe or this lobe. Here, this is the case. Suppose if the H2O is adds on the same side of the bromine, then you will get the retention of the configuration. If the H2O adds on the opposite side like this, opposite side to the bromine, then you will get the inversion of the configuration. That means here 50% of the retention of the configuration and 50% of the inversion of the configuration. This is called as a racemic mixture is formed. Sorry. See, in the SN2 reaction, there is a Walden inversion takes place, whereas in SN1 reaction, there is a racemic mixture or racemization takes place. Racemic mixture is formed because front side and back side attacks leading to two opposite configuration products, that is called two enantiomers. SN1 reaction of 2-bromobutane, either R or S, is a racemization process because of the nucleophilic attack from the either side is equal, which results equal amounts of two opposite configuration molecules, that is R and S2 butanol. Irrespective of this nature, whether it is R or S, but in the product, both compounds, R compound are also found, then S compound is also found. Now, Formation of an object and its mirror image products is equal proportion is called as a racemization. So in SN1 reaction involves the racemization process. Okay, the same another video also there. I will show you this video again. See this SN1 reaction. Rate determining step SN1 reactions. Substitution reaction. S for substitution reaction. N for nucleophile involving a nucleophile with one species involved in the slowest step, that is called as the rate determining step. This is going to be the alkyl halide. A bulky alkyl halide. This is the tertiary butyl bromide. And this yellow color one is said to be the bromine. Now, the nucleophile. See, I told you already, this is a two-step reaction. In first step, the bromine will be lost and formation of the, here because of this bulky nature. ఇదంతా బల్కీగా ఉంది కదా ఈ కార్బన్ చుట్టూ, అందుకని మనకి ఇటు నుంచి అప్రోచ్ అవ్వడానికి న్యూక్లియోఫైల్ అప్రోచ్ అవ్వడానికి అవకాశం ఉంది. Then before entering this nucleophile, first of all the bromide ion will be lost. 2-methyl 2-bromopropane. Now see here a loss of bromide ion and the formation of the carbocation is formed here. Here a complex first transition state and the bromide ion is lost and you will get a carbocation. It is a trigonal planar in shape, sp2 hybridization. It is a trigonal planar in shape. Then when OH is attacking, now the OH attacking, then you will get this is going to be the product. Okay, now again you can see this approaching. Now finally you will get the product. See, this is going to be this one, the alkyl halide. Now first it loses the what? A bromide ion, formation of the carbocation. Here the carbocation is formed. For this carbocation when formed after formation of carbocation, you know sp2 hybridization, then hydroxide ion is will, then it is going to be the product is formed like this. This is going to be University of Survey. They are prepared this one. That's why we are very much thankful to them. Now let us see this one. What is SN2 versus SN1? SN2 versus SN1. Let us see, these differences are very important. Characteristics of SN2 reaction. What are the characteristics of SN2 reaction? It is a single step reaction. Rate determining involves both that depends on both alkyl halide as well as nucleophile. It is a second order reaction. Rate is independent of the concentration of the strength of the nucleophile. Whatever the concentration of the nucleophile, it does not depend on concentration. It depends on the concentration. Transition state is formed with sp2 hybridized planar structure, not sp3d, because the carbon is having the 5 bonds. Transition state lo 5 bonds untai, but you don't think about the sp3d hybridization. It is only sp2 hybridization only. No carbocation intermediate is formed in the case of SN2. Whereas in the a leaving group is a strong, that is a weak base. The rate of a reaction inversely proportional to the bulkiness of the group attached of the carbon atom. That is going to be the methyl chloride is highly reactive towards the SN2 reaction compared to the ethyl chloride, and with increasing the bulky group, the SN2 reaction, the ease of formation, ease of undergoing SN2 reaction will be decreases with increasing the bulky group. Rate of a reaction is primary is greater than the secondary alkyl halide, it is greater than the third. Strong nucleophile performs SN2 reactions. Nucleophile attacks substrate directly from the backside. That's why you observe what you call as a Walder inversion. Polar aprotic solvents like DMSO, DMF, DMA favors SN2 reaction because that is polar aprotic solvent does not dissolve or solvent cations, and it dissolves only anions in solution. So by taking PAS means polar aprotic solvents, cations are removed and only nucleophile, only anion present to attack on the substrate. That's why only polar aprotic solvents are used. Walder inversion occurs in the SN2 reaction. Reaction is favored by low temperature, and high temperature leads to the E2 reaction. E2 means elimination by molecular reaction. That's why low temperature favors SN2 reaction. What are the characteristics of SN1 reaction? It is a two-step reaction. The rate of a reaction is directly proportional to only the concentration of alkyl halide. It is a first order reaction. Carbocation intermediate is formed. Rearrangement of the carbocation is also possible. Rate depends on the stability of the carbocation. That's why 3-degree alkyl halides readily undergo SN1 reaction compared to the 2-degree. It is readily undergo compared to the 1-degree. Rate of reaction is also depends on the stability of the cation and anion. Polar protic solvent. అక్కడ మనము apolar protic solvents అంటే ఇక్కడ మాత్రం polar protic solvents. These are called PPS. PPS dissolves both cation and anion because here the carbocation is formed. మనం SN2 reaction లో carbocation form కాదు. Leaving group should be a strong, that is a weak base, same as in SN2. Weak nucleophile performs SN1 reaction. Strong nucleophile will directly attack the substrate, resulting even reaction. Even ante elimination, unimolecular elimination reaction. Rate of reaction is independent of the concentration and strength of the nucleophile. It is independent of the concentration and strength of the nucleophile. Products are formed will be both R and S. That is called as a mirror images. Low temperature favors SN1. Even SN2 also low temperature favors. See, this is going to be the difference between the SN1 and SN2. Big barrier. Just 1 minute, please. Sorry for the interruption. See, rate law, SN1 and SN2. See, big barrier is, that is rate law is unimolecular, it is a bimolecular. And big barrier is a carbocation stability in SN1, whereas here steric hindrance in the SN2. Alkyl halides 3 degree, 2 degree, 1 degree for SN1. For SN2, 1 degree, 2 degree, 3 degree. The 3 degree are the worst, whereas in SN1, 1 degree is the worst. Nucleophile, weak, generally neutral in nature, strong, generally bearing negative charge in the case of SN. Solvent, polar protic, whereas here polar aprotic. Stereochemistry, inversion, mixture of retention and inversion will perform, that is racemization. But you observe SN2 is only the inversion of the configuration is found. The SN just now in the command cheppunnate, the SN2 reaction is concerted, means a single step reaction, whereas SN1 reaction is a stepwise reaction. And that is the same. See this one, The big barrier is nothing but, what is a big barrier? The steric hindrance is in the case of SN2 reaction, whereas the carbocation stability is in the SN1 reaction. In the table, just expression. The big barrier for SN2 reaction, okay, this already completed. Now here for SN2 reaction, the rate of reaction increases going from tertiary to the secondary to the primary alkali. Whereas SN1 reaction, the trend is in opposite. Here for SN2 reaction, primary is the fastest, tertiary is the slowest. For SN1 reaction, primary is the slowest, whereas the tertiary is the fastest. And another, this is for SN2 reaction, the rate of a reaction increases. Okay, this are. Remember that SN1 and SN2 reactions are only occur for alkyl halides and related compounds like tosylates and mesylates also. If the leaving group is directly attached to an alkene or alkyne, SN1 and SN2 will not occur. Remember, this is important part. That is, the leaving group, that is halogen, if it is attached to the alkene or alkyne, SN1, SN2 does not occur. The SN2 tends to proceed with the strong nucleophiles. The SN1 tend to proceed with the weak nucleophile. This we discussed here. The methoxide is stronger than cyanide.
సార్ ఎగ్జామ్ ఉంది సార్
రేపు ఎగ్జామ్ ఉందా?
ఇప్పుడు సార్
సార్ అది
ఈ రోజు ఎగ్జామ్ లేదు.
లింక్ పెట్టారు కదా సార్ గ్రూప్ లో. అది
22nd కదమ్మా. ఎగ్జామ్ ఉంటే నేనే బంద్ చేసేవాడిని. ఫాలో ఒక టూ స్లైడ్స్ ఉంది. యాక్చువల్గా ఎగ్జామ్ ఈ రోజు పెడదాం అనుకున్నాం కానీ కొంచెం లేట్ అయితేమో అన్న ఉద్దేశంతో ఈ రోజు ఎగ్జామ్ పెట్టలేదు. టుమారో 8:30కి 22nd ఉండే చూడండి.
సార్ 22nd ఉంది సార్.
అదే 22nd. అందుకని ఇంతసేపు ఎగ్జామ్ ఉండేది అంటే బై ఎనీ మీన్స్ 8 o'clock క్లోజ్ అవుతుంది. పాసిబుల్ ఉంటే 7:30కే క్లోజ్ చేస్తాము. ఇంకొకటి ఇప్పుడే చెప్తున్నాను వినండి. రేపు ఆల్కహాల్స్ ఈథర్స్ మీద టెస్ట్ ఉంటుంది. సాటర్డే రోజు కార్బోనైల్ కాంపౌండ్స్ మీద టెస్ట్ ఉంటుంది. సండే రోజు కెమికల్ బాండింగ్ మీద టెస్ట్ ఉంటుంది. రేపటి నుండి 3 days వరుసగా టెస్ట్ ఉంటాయి. ఒకటేసారి అన్ని లింక్ షేర్ చేస్తే మీరు కన్ఫ్యూజ్ అవుతారని రేపు టెస్ట్ అయిపోగానే ఇంకొక లింక్ షేర్ చేస్తాను. ఓకేనా?
ఓకే సార్.
ఓకే. See this, ఇందాక చెప్పుకునే ఇవన్నీ just this is going to be the SN2 versus SN1 reaction. In the case of SN2 you get the Walden inversion. In the case of SN1 this is going to be the racemidation takes place. One more important is I want to share a small video which relates to the both SN1 and SN2. వీడియో వచ్చిందా మీకు? ఒకసారి అబ్జర్వ్ చేయండి. ఒక ఇమేజ్ అయితే మీకు ఈజీగా అర్థమవుతుందని కొన్ని వీడియో ఫైల్స్ పెట్టాను. కెన్ సీ హియర్. Is it SN1 or SN2?
SN2 sir.
SN2 reaction. This is going to be the SN2 reaction. The leaving group is the right side. The entering group is on the back side. Therefore, this is a transition state. Now see the compound is opposite configuration. This is going to be the opposite configuration. Now you can see now SN2 reaction, SN1 reaction. See, this is an energy profile diagram of SN2 reaction. Energy profile diagram. This is going to be the transition state, and this is going to be the product form. See, this is going to be the bromide. This is going to be the counterclockwise and S configuration. Okay, we'll get again this one. This is going to be the alkyl group. Okay, this is the incoming group. This is the first step is the ionization step. And this is going to be the water or a nucleophile that is attacked on this carbocation. Then the proton is lost. Then here it is the OH. Now here what happened? At the same side of the bromine, the OH is added. That is the retention of the configuration. This is called as a retention of the configuration. This video was made by CV Kalyan Kumar, and we are very much thankful to him. See, this is going to be an energy profile diagram where it has the two peaks. Now it is approaching the nucleophile and you are getting this. This is the loss of the proton from the oxonium ion. Okay, this is again repetition. Okay, let us. See now, how does this Walden inversion takes place? This is going to be the carbocation formation, and it is having the free rotation. And this is going to be the center carbon, which is having the positive charge. See, one is attacking on the opposite side of the leaving group, another is attacking on the in the same direction in which the leaving group is present. Then finally, you get this compound and this compound. This is the retention of the configuration. Okay, this is a repetition. That's okay. Now what happens finally? This is going to be the retention of the configuration. This is going to be the configuration opposite to this inversion of the configuration. See this. The nucleophile can attack on both sides with the same probability. With the same probability. One may attack on the same side from the leaving group. One may attack on the other group. This is another one. It is opposite to the leaving group. That's why you will get the opposite configuration with this. That's why that is a repetition 2 times. Okay, in this way you can understood this what is this configuration. Thanks for watching this one, and we are very much thankful to the person C. Kalyan Kumar Garu who made this wonderful video to understood this what is called as the okay. With this we can conclude our discussion, today's discussion. Thank you all for listening patiently. Babam Dada 2 hours only patient ga vintunnaru kashtabadi. I hope it will be useful to you. Thank you, one and all. With this, I can
Thank you,
conclude this session. Tomorrow, there will be a test at 8:30. Ethers, alcohols, ethers, and phenols. Day after tomorrow, carbonyl compounds, and in Sunday, chemical bond. Okay. See you.
Sir.
Okay. Chepandi, ఏమైనా doubts ఉంటే